You ever just stop and think about the absolute magic happening inside your computer right now? I mean, you've probably got your browser open, maybe some music playing, your email. How on earth does it all run at the same time without just completely crashing? Well, today, we're going to peel back the curtain on your computer's incredible secret juggling act. So, this is really the big question we're tackling. It just seems impossible, doesn't it? How can one single CPU core be thinking about so many different things at once? Well, the answer isn't magic, but it is something just as clever. It's a whole system of incredibly fast task switching, all governed by some very smart rules. And this slide right here, this is the secret sauce. A program or a process, which is the technical term, it's actually not working 100% of the time, not even close. Its life is this constant back and forth cycle. You see it here. You've got these CPU bursts, that's when it's really thinking, crunching numbers, but then it hits an I/O burst. And I/O just means input-output. Basically, it's waiting. It could be waiting for you to type something, for a file to finish downloading, whatever. And that's the magic moment. In those tiny little gaps of waiting, that's when your computer squeezes in all its multitasking. So, who's managing all this stopping and starting? The operating system, of course. Let's think of your CPU as the master chef in a crazy busy restaurant kitchen. It can only cook one dish at a time. And to keep that whole kitchen from descending into chaos, it needs two key managers, the scheduler and the dispatcher. Now, these two roles, they're different, but they work together perfectly. The scheduler is kind of like the head waiter. He's looking at all the food orders coming in and deciding, okay, which one should the chef make next? Which one's most important or quickest? He makes the big picture plan. Then you've got the dispatcher. He's the kitchen assistant who actually does the work. He takes the finished dish from the chef, clears the station, and immediately hands in the ingredients for the very next order. It's that simple, really. The scheduler decides, the dispatcher does. And the dispatcher's job is insanely fast and precise. It's this little three-step dance. First, it switches the context. It carefully saves everything the current process was doing, like putting a bookmark in a book, and then it loads up the save state of the next process. Second, it switches the CPU from kernel mode, where the OS is in charge, to user mode, which basically means it's handing the keys over to the application. And third, it jumps to the exact spot where that program last stopped, so it can pick right back up without missing a single beat. Okay, so here's a crucial point. That switch isn't instantaneous. The little bit of time it takes to do that three-step dance is called dispatch latency. We're talking microseconds here, which is ridiculously small. But when your computer is doing this millions of times a minute, those microseconds really start to add up. Having a fast dispatcher is absolutely key to making a computer feel snappy. All right, so if the scheduler is our head waiter deciding which order to cook next, how do we know if it's actually making good decisions? How do we measure if our kitchen is running efficiently? Well, there are a few key ways we can measure that success. First up is throughput. This one's pretty straightforward. How many jobs or processes are we actually finishing every second? In our kitchen analogy, it's just the total number of dishes served per hour. And the goal is simple. You want to maximize throughput. Get as much work done as possible. Next, we've got waiting time. This is the total time a process spends just sitting there. It's in line, it's ready to go, but it's just waiting for its turn on the CPU. Think of this as how long a food order just hangs on that ticket line before the chef even looks at it. For a system to feel smooth, you want to minimize this, because time spent waiting is pretty much wasted potential. And that brings us to response time, which is so important for how fast a system feels to us. Now, this is different from waiting time. It's not about finishing the entire job, it's all about starting it. So when you click an icon, response time is the time it takes until you see that first sign of life from the app. For a restaurant, it's how long it takes for the customer to get their appetizer or even just a glass of water. A low response time is what makes the system feel really interactive and responsive. Okay, so let's check out our first scheduling strategy. The most basic way you could possibly decide who's next is simple. First come, first served. It's literally just a line. Whoever gets there first gets served first. Super fair, really easy to build. But, as we're about to see, it has a massive, massive flaw. And this slide just nails the problem. It's called the convoy effect. Just imagine you're at the grocery store. All you have is a single bottle of water. But the person in front of you, they've got 3 shopping carts just overflowing with stuff. You and everybody else with just a few items are completely stuck waiting for this one gigantic job to finish. For a computer, this is an absolute disaster for efficiency. You've got all these small, quick jobs just sitting there, ready to go, and the CPU is just tied up. It's not being used well at all. So how do we fix this convoy effect? Well, with a much smarter strategy. Instead of just a simple line, what if we could let the person with just one item cut to the front? That's the whole idea behind the shortest job first algorithm. So the rule is simple. Whenever the CPU becomes free, you give it to the process that has the smallest amount of work to do next. This immediately breaks up that convoy and dramatically improves the average waiting time. It really seems like the perfect solution, but yeah, of course there's a catch. And it's a pretty big one. And here it is. This is the catch. How in the world can the scheduler possibly know how long a process is going to need the CPU for before it actually runs it? It can't predict the future. This is the fundamental, massive challenge of the shortest job first algorithm. Now, in practice, systems try to guess this based on what the process did in the past, but it's never going to be perfect. And just to add another layer to this, the strategy comes in two different flavors. The non-preemptive version is, well, it's polite. Once a job starts, it gets to finish its current little bit of work, even if a shorter job shows up. But the preemptive version is much more ruthless and, frankly, more efficient. If a process is chugging along and a new, even shorter process arrives, the scheduler will just interrupt or preempt the current one, save its progress, and immediately run that new, shorter job. This preemptive version is also sometimes called shortest remaining time first. So let's just take a quick step back and think about all this. We've got processes constantly switching between working and waiting. We have a scheduler making decisions based on different rules, and we have a dispatcher making the actual switch happen in microseconds. All of this is happening completely invisible to us just to make your computer work. It's this constant, incredibly high-speed dance of processes. And that kind of leaves us with one final thought. We've only looked at two really simple dance routines, first come, first served, and shortest job first. But modern operating systems use way more complex rules, trying to balance getting short jobs done quickly while also making sure the big, long jobs don't get ignored forever. So the real question is, as this invisible dance happens millions of times every minute, what really happens to your computer's performance when you start to change the steps of the dance? Something to think about.